Hi, CNT140. We are on our fiber optic book, Chapter 2. So this chapter is all about some terminologies and jargon that we run into as we're dealing with fiber optic. So kind of the language of fiber optics, measurements, specialized fiber optic terms that we run into. This chapter kind of reminds you, hey, use this chapter to reference as needed as you're going through reading about or learning about other areas. Use this almost as like a reference to look things up as you need them. Reminding fiber optics is sending signals from one location to another through that thin glass fiber. The signals can be analog or digital, can be voice, data, video, lots of capabilities here. Fiber can transport more information longer distance in less time than copper, wireless, and other mediums that are out there. They remind us about the metric system. Pretty much everything we deal with in fiber optic is in metric. Fiber optic cabling is measured in lengths by meters, and a lot of times by 1,000 meters at a time, so a kilometer. So remembering the kilometer is 1,000 meters. We run into millimeters when we're dealing with the diameter of fiber optic ferrules as well as buffers and so forth, 900 millimeter buffer and that sort of thing. So millimeters is 1,000th of a meter, 1,000th of a meter. When we actually look at the fiber itself, we start talking in microns, 1/1,000,000th of a meter. 25 microns is about 1,000th of an inch. Maybe around 50 microns is 2/1000ths of an inch. We're now starting to get to like the thickness of a piece of paper, just to give you a little bit of a perspective there. The core diameters of fiber are the first number we see when we look at a fiber optic size. The cores will be 9, 50, or 62.5 microns. The cladding, on the other hand, is always going to be 125 microns. 125 microns is, again, that's about the thickness of a piece of paper. A little bit thicker piece of paper. Nanometer is what we use to measure or reference the wavelength of light that's moving through the fiber. So nanometer is 1/1,000,000th of a meter, 1/1,000,000th of a meter. This gets used to reference the wavelength of light. 850 nanometers or 1,300 nanometer wavelength light source. The fiber itself is made up of a couple basic parts, the core and the cladding. The core and the cladding is all glass, so when I'm looking at the actual glass stub, I'm seeing the cladding, but inside is the core of the fiber. That is where the light is actually traveling. Around the outside of the fiber is typically buffer. Not every fiber optic cable is like that, but a lot of the ones we would deal with in premise cabling would have a buffer around the outside, which almost kind of reminds you of insulation. The fiber itself, the core is where the light is being transmitted. The cladding is there to kind of act like the gully to keep it in the core. That's what it's actually doing. So as I launch the light into the fiber, the cladding is keeping the light in the center of the core. If I look at the construction of fiber, again, this part out here, this is the glass stub. The core is through the middle of the cladding. We have the coating, that's your buffer coating that's around the fiber for protection. When we deal with fiber, we talk about mode. Mode is basically a ray of light. So as I'm sending a signal down the fiber, if I have multiple rays of light representing that one, it's a multi-mode fiber. So that pulse we're sending down the fiber to represent a 1, that pulse of light we're sending down the fiber to represent a 1, is made up of multiple modes, multiple rays of light. That would be a multi-mode fiber. On the other hand, if I send a pulse of light down the fiber, think about a laser light. That is a single mode, a single ray of light, single mode of light down the fiber to represent that 1. That is a single mode fiber. That's a single mode fiber. Multi-mode fiber has the larger core, typically 62.5 or 50 microns. Your 62.5 is your step index. Meanwhile, your 50 is your graded index. With these are designed for 850 or 1300 nanometer wavelength light sources, so shorter distances. Typically your backbone connections between your closets. That's what these get used for. Your step index is the larger core diameter, and it's going to almost, as you see here, almost act like a reflector and bounce the light, bounce the modes of light down the fiber. Meanwhile, the graded index down here, I don't know if I have that here. There's your step index. Okay, there's your step index. It's actually kind of bouncing the rays of light down the fiber. That's your 62.5. Meanwhile, the graded index is going to bend the light back into the fiber, a lot more gentle on the way it's sending the modes of light down the fiber. And that is your 5125. 5125, that's your graded index. Meanwhile, single mode, we have a much smaller core, 8 or 9 microns in diameter. So therefore, we're sending a focused ray of light down there, a single focused ray of light down there to represent that one, that single pulse, if you will. This now can go much greater distances, so this tends to get used for phone long distance connections between maybe cities or around the city, and maybe even from your provider out to the side of your home, fiber to the home. So these are using laser light sources in the 1310 to 1550 nanometer wavelengths. As I like to say, longer wavelength, longer distance. Longer wavelength, longer distance. That's something to kind of keep in the back of your brain. So with your single mode fiber, they're making the core so much smaller that you basically have one ray of light, one mode of light traveling down the fiber to represent that one. We identify fiber by those relationships, the core to the cladding. So a 5125 multimode fiber, that's your graded index. Your 62.5125 multimode fiber is your step index. And then your 9125 is your single mode fiber, that very small core diameter. Most of your fibers that we're going to deal with have an outside diameter 125 microns. You notice that number has stayed the same. I put all these again together in one spot for you, and then I even put the kind of the cross section out here so you could see the 62.5 step index, the 50 graded index, and then your 9 here, your single mode really small core, and I kind of give you a kind of a relationship between them. That's an approximate representation of the larger core, kind of a little bit smaller core, and then the teeny tiny core. As I always like to say, this is like garden hose versus coffee stirrer. You know, if you have to like kind of visualize the difference. They also do mention the plastic optical fiber. These are usually short distance for connections between TV or audio systems. And you see here that's a lot larger plastic fiber optic connection. The cables we're dealing with can be tight, loose, or ribbon cable, tight buffer, loose tube, or ribbon. So as we look at these, hopefully these pictures look familiar from before. Your tight buffer cable is this kind of zip cord cable. If I look at that individual strand there, that individual strand is your 900 micron buffered fiber. All right, 900 micron buffered fiber. That almost like it's almost like another insulation around the fiber. That would need to be stripped off before terminating. And again, this is typically indoor use, mainly indoor use, like backbone between your closets, if you will. The loose tube, it is actually a tube where the fibers are in there, almost like, you know, a bunch of straws in a cup, if you will. That is typically used for burying underground, that sort of thing. So you have these fibers, there's no buffer on them, and they're in this tube kind of freely moving around. And then there is actually ribbon fiber as well. So a flat cable here with a whole bunch of fibers next to each other, almost like, you know, crayons in a box kind of thing. This you have a high capacity of fibers in a small space. When we're dealing with fiber, we look at jacket and the strength members. Here's some terms we run across. The jacket is the outside covering for protection from the elements. And then the strength member are the fibers inside, typically Kevlar. It's a brand name we would recognize, that are there for tensile strength. They're also there for tying onto to pull the cable through conduits and so forth. So with our jacket, remember the fire rating. General riser plenum, look at that last letter. So OFN-R riser, that could be installed between closets vertically in a building. P, OFN-P for plenum, being installed in plenum spaces. As I look at the cross section of the fiber, core cladding, there's the buffer. Here is the strength fibers. This almost reminds you of hair, real fine hair, almost like doll hair kind of thing. Those strength fibers are there for tensile strength, and they're also there for you to tie onto for pulling the fiber cable through conduits and the like. When I deal with fiber optic cable outside, we tend to run into cabling that has armoring. This armoring kind of reminds you of a thick foil shield, and it's really there for protection from elements like the weight of soil and things on top, as well as for discouraging critters from chewing through. If you've ever dealt with squirrels or mice, you know what I'm talking about. They tend to chew through things like this, so this is there to try to deter that or protect that. Our outside plant fiber installs usually fall into 4 categories: underground, direct burrow, aerial, or submarine. So if I look at underground cabling, they're showing you here that this is your buffer tubes. So these are usually loose tube cable in the buffer tubes, and then this can be installed in conduits and things underground, ducts underground, that sort of thing. If I'm going to direct bury the cable, I'm typically going to use this armored cable, and that's there again to prevent the weight of soil and so forth from damaging the cable, as well as rodents and critters from chewing through. If I'm going to install aerially between telephone poles, I'm going to use a cable that usually has a strength member in, like a steel cable here. That's what you're seeing here. This steel cable can get anchored to the telephone poles. That's going to take the weight and support the weight. And this insulation on the outside almost looks like a figure 8. This part down here almost acts like a little hammock to hold the fibers, so the tensile strength is not pulling on the fibers. The cable is taking the weight. The fibers are going along for a ride. If I'm dealing with installing underwater, I'm going to deal with submarine cable. As we look here, here's a couple samples of underwater cabling, and you see a lot of layers of armoring for, there's a lot of layers of insulation for keeping the water out, but then there's also layers of armoring to resist the weight and the pressure of the water that's on top of it. Here's a reminder of a bunch of undersea cables. Here's maps of undersea cables that are installed. Again, another map reminding you of lots of undersea cables that are installed, and a picture of installing and giving you an idea of the size of. And the design does need to resist, especially in shallower waters, needs to resist critters from chewing on. When we deal with fiber optics, we often run into connectors. The connector is that I'm terminating the fiber and putting a connector in to allow me to plug it into, whether it be plugging into a patch panel or a device allowing me to plug into. So as I look at the connector itself, it is actually a handful of pieces that we're using to make the connection. Later this semester when we terminate, I'll show you all those up close and personal. Do remember there's different styles of connectors. Once upon a time, ST was very common. Then LSC became much more common and used for quite a while. The most common one right now is your LC fiber here. The next couple slides, I have close-ups of each one so you can see them up close and personal. That way you can tell them apart. And then there's your LC fiber connection right there. Looking at the connector up close, you start seeing the various parts of. Here's the outside connector body, and here's the ceramic ferrule. And then down the center, right above my pointer, that little teeny dot is the actual fiber itself. So we're talking some very small piece of equipment here, if you will. So there's your fiber connector. When we come back, we'll start talking some splicing.